Hi, everybody. This is Elizabeth Wilson from the Irving Institute of Energy and Society at Dartmouth College. And I'm really excited today to share our speaker and our series. While I'm hosting this meeting, this series of New Energy Conversations with Early Career Researchers is a collaborative effort with colleagues from the below institutions. And what's been so satisfying for all of us is the incredible talent of young researchers and our desire to give them a forum to share their research with all of us at a time when none of us can travel. And so today I'm very excited to have Dr. Parth Vaishnav, who will be speaking currently at Carnegie Mellon, soon to be joining the faculty at University of Michigan, and who will be speaking on Electrify Everything and looking at 2 case studies. And I know this is a topic of real interest to our audience, of real interest to our students, of real interest to our community. And so with that, I turn it over to you, Parth. Thanks very much. We're really looking forward to this.
Thank you very much. This is a great idea, and thank you so much for the opportunity to do this. The title of this talk reflects the idea that is popular among some climate advocates that we need to electrify virtually all sectors of the economy in order to decarbonize it and avert dangerous global warming. I'll present 2 cases in this talk that examine how electrification may play out in the real world. I'll start out with a high-level outline of the talk. I'll first situate my research interests in general, and I'll situate the topic of this talk within those interests. What I'm really interested in is in understanding how technology works in the real world, where it confronts economic, political, and behavioral constraints. And then I'll discuss 2 studies. The first asks whether the 2 technological trends in light vehicles, their electrification and the notion that they may become substantially automatic in the future, are in sync with each other. And the second study looks at the consequences of the electrification of space heating in the United States for the climate, for human health, and for people's heating bills. So to start with a bit of background about the type of work I do, in my first few years at the Department of Engineering and Public Policy, where I got my PhD, I worked on a few problems that dealt squarely with the problem of sustainability, specifically the sustainability of the transport system. Early in my time as a postdoc, I got involved in a series of studies about regulating additive manufacturing in civil aviation. As a direct result of that work, I'm now involved in a couple of projects which are focused on broadly the economics and industrial ecology of additive manufacturing. The more recent work deals with questions related to sustainability of the electricity sector, and on the electrification of sectors that currently involve the distributed combustion of fossil fuels. So you can't easily decarbonize them by capturing CO2 emissions. In much of my current and planned future work, I'm interested in understanding what happens at that intersection if you add increased automation to the mix. So the 2 studies that I'll talk about today and which form the basis of much future work lie at the intersection of those 3 topics. With that, I'll dive into the meat of the studies. The first one asks the question, can autonomous light vehicles also be electric? This just came out in Nature Energy this Monday. The paper was written with my student Anirudh Mohan, who led the work and whom I advised jointly with Professor Venkat Viswanathan, who's at Mechanical Engineering here at Carnegie Mellon, and Shashank Sripad, who is one of Venkat's doctoral students, also in Mechie. And this is the motivation for the question. As of about 2014, transport surpassed the electric power sector to become the largest source of greenhouse gas emissions in the US. About 60% 60% of those emissions come from light vehicles. and a recent review that tried to describe what a net zero economy would look like concluded that light transport was actually easy to decarbonize. You just had to electrify it using clean electricity. This is a pie chart which shows the share of CO2 emissions from fossil fuel combustion across the globe.
Excuse me, Parth, right now we can't see your screen.
Oh, wow.
So
I'm sorry.
Yeah, that's okay. I just wanted to make sure that we were able to see it. I didn't know if you were just doing an intro.
Oh, no. I apologize. I have no idea what happened there. It was on a second ago, wasn't it? Okay. All right. Sorry about that. That should work. Is it visible now?
This is perfect, and they're really super slides. So if you, I think it was the table there. There's the pie chart you were just talking about.
I'm awfully sorry about that. I did not realize it was not showing. So this was a graph which shows the trend in CO2 emissions, and as of 2014, transport overtook power generation. And this is the chart from the Davis et al. Paper that was published in Science a couple of years ago, which shows the share of greenhouse gas emissions from different sectors across the globe. The small wedges are things that the authors think are at least technically straightforward to decarbonize, and short light transport is one of the things that they believe can be decarbonized easily. And the wedges that stick out are the things that are hard to decarbonize, and sort of tellingly in there is load following electricity, which they acknowledge is difficult to decarbonize. So in this study, we accept the premise that light vehicles must eventually be electric in order to decarbonize them. And we ask whether it's compatible with the idea of greater automation. Part of the motivation for this comes from the anticipated safety benefits of automation. Around 37,000 people die in automobile accidents every year in the United States, and perhaps machines can do better. This is not a new idea. This ad, which is from 1957, ties the concept of autonomy to electrification. This ad was taken out by the electricity industry back then in 57. Now, the ultimate premise of autonomy is that we will reach level 5, which currently exists only in artist impressions, but which may look like this, where you might actually be able to go to sleep, read a book, and the vehicle will drive you from origin to destination without your ever having to intervene in any situation. So the question is, in the near term, can you have both those things, electrification and autonomy? Ford thinks you cannot. It thinks that the first autonomous cars will be hybrids. They don't think fleet operators will be willing to sacrifice range for autonomy. So I think that's an Argo autonomous vehicle driving on the streets of Pittsburgh. And that statement by Ford earned them a very sharp rebuke by Mary Nichols, the chair of the California Air Resources Board. And it has to be said that not everyone in industry agrees with Ford's position. GM, for example, has built its AV platform on the all-electric Chevy Bolt. So which one of these two points of view is right? And that's the question that we're trying to resolve. To get to that, first we have to recognize that the autonomous vehicles that are on the road today look nothing like that sleek Volvo or even the open-top cars that we saw in the 1957 ad. They look like this, and there are vehicles driving around in Pittsburgh like this, and in fact in Ann Arbor as well. They have sensors which mess up their aerodynamics. they have, those sensors consume power, they add weight. One thing that turns out to be very important, as we'll see, is LiDAR. Conventional LiDAR uses laser pulses to build a representation of the vehicle surroundings. And if you want to see all around the vehicle, the laser has to be mounted fairly high atop the vehicle. And a consequence of that is that you pay a big price in terms of aerodynamic drag by having this big sensor stick out from the vehicle. You need computers that soak up a lot of energy to process the data that comes from the sensors. The saving grace might be that these vehicles might drive more smoothly than human drivers do. They might be less prone to sudden acceleration and braking. What makes this especially challenging for electric vehicles is, of course, they have heavy batteries. What you see here in this picture is the chassis of the Tesla Model S, and that is the battery there. This is a car that weighs around 4,600 pounds, out of which 1,200 pounds, or about a quarter, is the mass of the battery. In contrast, a full tank of gas in my Honda Accord is 90 pounds and gives the car a far greater range than the Tesla Model S in this picture. So the question is, given that any extra energy has to be supplied from a battery that is still too heavy, can you power all the paraphernalia of automation without paying a huge price in terms of range? To answer that question, we use a physics-based model to work out what the vehicle range is. We take a second-by-second velocity profile that's developed by NREL. We take information about the battery, the vehicle's characteristics, both its mass and its aerodynamic characteristics, and we run that through a physics-based model that I'll describe in a second. And effectively, we run the velocity profile until the battery runs dry, and that gives us the range of the electric vehicle. We then modify this process for an autonomous electric vehicle. We add computing load. We smooth out the velocity profile in a way that I'll describe in a moment. We add the mass of the sensor. We account for the change in drag coefficient because of that LiDAR, if you have LiDAR. And we include the electricity consumption associated with the sensor. And we run it through the same physics-based models, slightly modified, to calculate autonomous electric vehicle range, and then we compare the two. So this is a description of the physics-based model. At any instance, the amount of power that is needed to propel the vehicle is a sum of the amount of power it needs to overcome drag, which depends on its aerodynamic characteristics and quite a lot on its velocity. The amount of power it needs to overcome friction, which depends on its mass and its velocity, and the amount of power it needs to accelerate, which depends on its velocity and how quickly that velocity is changing. All those things get summed up and get adjusted for the fact that the battery is not fully efficient and the drivetrain is not fully efficient. Now this gets modified for autonomous electric vehicles in the following way. We change the velocity to a smooth velocity profile, which means that we also change the acceleration every second. We change the drag coefficient of the vehicle. We assume that the change to the frontal area is pretty small. And we adjust the mass of the vehicle to account for the fact that now it's carrying sensors and LiDAR and so on. Turns out not to matter very much. And to that, we add the power requirements associated with computation and sensors and correct those for the round trip efficiency of the battery. So I'll start by describing the velocity profile. We run it for a couple of different driving scenarios. One is a city highway hybrid and one is a city velocity profile. The city highway hybrid includes moments when the vehicle is notionally on the highway. So this is when it's doing sort of 50, 60 miles an hour. You don't have that kind of acceleration you don't have that kind of speed in the city profile. And then we smooth both those profiles. So I'll give you an example of how we go about doing that. What you see here is the city highway composite profile. The blue profile is the original profile, and the red one is the smooth profile. We use a spline smoothing function to smooth the velocity, and that function has two components. So on the one hand, you want to maximize fidelity to the original velocity profile. You want the vehicle to start and end at the same places, be stopped at the same places. And on the other hand, you have a penalty for acceleration. So the actual term we use is jerk, which is the rate of change of acceleration. And the objective function sort of trades off between these two components. And we use a parameter to tune that trade-off such that we generate a series of velocity profiles that give us different levels of energy saving. So the velocity profile that you see here is tuned to yield a 10% energy saving relative to the original profile. And you can see how it does that by zooming into a couple of minutes of that profile. As you can see, there are moments when the car is either braking or accelerating hard, that the smooth velocity profile changes the original velocity profile the most. And here you can see the effect of that change on power. There are a couple of things that are noteworthy. The biggest difference is when the vehicle is accelerating very quickly. So at this moment, there's rapid acceleration. There's a sharp increase in power, and the smooth velocity profile sort of cuts it down. Where you actually pay a penalty is that when the vehicle is stationary, you consume no power if this was just an EV, but in an autonomous vehicle, we assume that you still consume some power because you're computing. The vehicle still has to sense its surroundings and plan. There are a range of estimates for the computing power needed for automation. They span an order of magnitude in the literature. This is essentially an open question. NVIDIA has a chipset that claims it can do full autonomy for 500 watts. Tesla has a chip that it claims can do full autonomy at 75 watts, but Tesla is allowing for dual redundancy, and so that adds up to 150 watts. And there's a large number of combinations of sensors, which we describe in the paper, that you could potentially use for autonomy. We model that as a power load of between 30 to 150 watts. And what sensors you use and how much load they have depends on whether or not you use LiDAR. There are a couple of players in the market who don't want to use LiDAR or would like to use solid state LiDAR, which consumes a lot less energy and has a smaller aerodynamic penalty. So we'll model that. We also tried to find empirical estimates of the drag penalty associated with all these sensors, and we did not find anything that was public. So we tried to approximate that by a bunch of other things that people put on cars. And we reasoned that if you had LiDAR, it would be somewhere between having a police siren, which is here, and somewhere between having a barrel stacked on your car. And we've done a bunch of simulations which suggest that the stack up here is much more like a barrel than like a police siren in terms of what it does to the aerodynamics of the car. And of course, we recognize that all of this is uncertain. We assume that these values take uniform distributions between these bounds, which we've got from the literature. We also assume that computing load and sensor load are perfectly correlated with each other. After all, the computer has to process what comes from the sensors. And we've assumed a fairly wide range in the change in drag coefficient due to LiDAR. So here are the results for the composite driving profile. This is the result of a Monte Carlo simulation using the distributions that you just saw. The black line here is the range for our base electric vehicle, which was a Tesla Model 3. If you had an autonomous electric vehicle with LiDAR, so with that aerodynamic profile, you end up with this blue distribution here. And this blue line is the median range of such a vehicle. And if you could do away with LiDAR, you end up with this orange distribution here, and this orange line is the median of that distribution. So the median loss in range is 9% with LiDAR and 4% without it. With LiDAR, the range exceeds that of a non-autonomous EV in only 5% of our simulation. So this is when you get enormous savings from smooth velocity profile, but all your compute and sensor load and so on are quite low. If you don't have LiDAR, in about 25% of our simulations, you end up with an autonomous vehicle that has greater range than a standard electric vehicle without autonomy. So those were the results for the composite driving profile. These are the results for the city driving profile. By and large, the loss of range is slightly lower in the case of city driving. Now, different things affect range in different driving scenarios. So in the case of highway driving, the drag is more important. So going from no LiDAR to LiDAR affects your range by 5 percentage points if you're doing city highway driving, but only by 3 percentage points if you're doing city driving. This makes sense. Your velocities are typically lower in the city, so you pay a lower drag penalty. And if you shift it to a much more efficient computing solution, that matters a lot for city driving because velocity is low and the computing is on all the time, regardless of how fast you're going. So you have a 9 percentage point increase in the range impact if you go to the less efficient computing solution in the case of city driving, and that impact is only 6% for the city highway composite driving. We also modeled how quickly the battery degrades. Since you're drawing more energy from the battery, presumably you'll need to charge it more often. And these are the results. So the black line over here, which is sort of hidden by the silver line, shows the battery degradation for an electric vehicle over its lifetime. So the state of health of the battery, which is the maximum charge it can hold relative to what it could hold when it was new, falls to about 80% at the end of about 110,000 miles. For the median autonomous electric vehicle, that number is only slightly smaller. It corresponds to being able to drive the vehicle for 6 or so months less over the 10-year life of the vehicle. So it's not an enormous impact. And it's actually possible to envisage a scenario where the effect of velocity smoothing is so great that you actually increase vehicle range with autonomy. Now, it's hard to know how much people might value that 30 or so miles in range that they would have to give up if they had autonomy. There are a couple of simple lines of reasoning that you could follow. So the first is that if you compare near identical cars that differ only in terms of their range, you would conclude that people are unwilling to pay more than about $100 per mile of range. And consumer surveys sort of show that the number is in that ballpark. Of course, it's even harder to know what people will pay for full autonomy. After all, no one has experienced it. Autonomy is arguably a bit like having a chauffeur or an Uber driver. And the Bureau of Labor Statistics says that people in those professions get paid about $12 an hour. This is this is not what you pay Uber. This is the part of what you pay Uber that ends up with the driver. So it's about $12 an hour. This is what people will pay not to drive. And so if you assume that I somehow need to get to the $3,000 that I'm going to lose because I now have less range, I would need to save about 250 hours of time to get to those 3,000 hours. Now, the average American drives about an hour every day. So it's not hard to imagine that the value of the time that you are not driving actually exceeds the value that you place on that loss in range. This is admittedly a very approximate exercise, but the estimates in the literature for what people are willing to pay for autonomy, which use more sophisticated surveys, basically vary again by an order of magnitude. Hard question to answer. So our conclusion was that automation will impose an energy penalty, but it is not incompatible with electrification. Automakers would benefit from investing in LiDAR-free or solid-state LiDAR solutions. Future research should account for the fact that these vehicles will be deployed very differently from current vehicles. So for example, the issue of range might not matter if you did not have a human driver to experience range anxiety. So if these things were just operated as fleets, then range may not matter that much. And the fact that you can have both autonomy and electrification may be a bargaining chip that policymakers might be able to use to say that, look, if you want to test in my city, if you want to test your autonomous vehicles in my city, you need to show me a plan which says that the production vehicle version of your vehicle will eventually be electric, because I know you can achieve both. So that's one policy insight. With that, I'll shift over to the second study, which has to do with space heating, which is responsible for about 5 to 6% of US greenhouse gas emissions. This was a study that I undertook with a master's student in our energy science and technology policy program, and with any luck, it will be published relatively soon in environmental science and technology. Again, the study that I spoke of earlier, which just tries to describe a net zero energy system, argues that it is in fact easy to decarbonize space heating, which technically speaking it is. You just have to electrify it. And in fact, this has got quite a lot of traction with policymakers. There are municipalities and the entire Netherlands which want to get rid of natural gas in buildings with the idea that they will electrify space heating and cooking and so on. And an efficient way of doing this is to use electric heat pumps. Heat pumps are an air conditioner running in reverse. They use a refrigerant to extract heat from the cold ambient air and move it against the temperature gradient to a warmer place. The laws of thermodynamics say that in order to move heat from a place of low temperature to high temperature, you have to do some work on the substance that's affecting the transfer. And that work is done by an electric compressor in a heat pump. The good news is that the amount of electricity you have to supply is a fraction of the amount of heat that you can actually move. So you might be able to transfer 3 kilowatts of energy and spend only 1 kilowatt to affect the transfer. That 1 kilowatt also is available as heat because it compresses a gas. So you get 4 kilowatts of heat for the price of 1 kilowatt of electricity. And the ratio between these two quantities, the total amount of heat that you get divided by the amount of energy that you supply, is called the coefficient of performance of a heat pump. And it's typically substantially more than 1. This analysis asks what would happen if you went from using the current mode of heating, which we assume is natural gas or resistive heating, to heat pumps at different locations in the US. I ran this analysis for 883 locations across the US. So the results will sort of summarize the findings from that analysis. I've looked only at natural gas and resistive heating because there is a bunch of past work that suggests that compared to propane and fuel oil, heat pumps are both cheaper and better for the environment. So I'll briefly describe my methods here. The laws of thermodynamics also say that the coefficient of performance of the heat pumps falls with ambient temperature. And so based on data from different commercially available models of heat pumps, I calculated how the coefficient of performance varies with temperature. And then I found the typical hourly ambient temperature for each of those 883 locations in the study. And combining those two things, I got the coefficient of performance for a typical heat pump at each of those locations in every hour of a typical year. I combined that with the heating requirement in a typical single family home at each of those 883 locations. And that gave me the electricity used by the heat pump during every hour of a typical year. Over the years at Carnegie Mellon, we have created and refined a data set that tells us how much environmental and health damage in dollars a marginal kilowatt hour electricity demand during a given hour of day, during a given season, and in an electricity region produces. Combining all of this tells me how much damage to the environment I would do from using that additional electricity to energize the heat pump during every hour of the year. I then calculated how much damage natural gas combustion would do in a furnace, and then compared the two to calculate what the effect of switching to heat pumps would be. So here are the results. Each of these points that you see here represents one of the locations that we analyzed. So there are 883 points here. They're color-coded to correspond to the NERC regions in which the location is. So for example, all the yellow points are WEC, the Western Electric Coordinating Council. They're also shape-coded to signify what the current heating fuel is. So you're shifting to heat pumps from what? If it's a circle, you're shifting to heat pumps from natural gas. If it's a triangle, you're shifting to heat pumps from resistive electric heat. On the x-axis is the benefit that benefit per household in dollars per year that would accrue in terms of reduced criteria pollutant emissions. So if the number is negative, it means heat pumps produce a worse outcome. Similarly, on the x-axis, you have the benefit from reduced CO2 emissions from switching to heat pumps. And again, if the number is negative, it means heat pumps produce a worse outcome. What you see is that except in parts of the South, except in the Northeast, and except in parts of the West, in particular the Pacific Northwest, a switch to heat pumps increases CO2 emissions if your original fuel was natural gas. What this also shows is that except for places where we currently use electricity for heating, heat pumps would do even more serious damage from increases in criteria pollutant emissions. The red line here is a 135-degree line. Anything above this line is a net benefit for the environment. As you can see, there are no circles above this line, although some parts of California and some parts of the Northeast do come close. So what this means is that there is an environmental benefit from going from resistive heating to heat pumps, but there's not an environmental benefit almost anywhere in the US for going from natural gas to heat pumps. This chart is similar to the one that you saw, except that on the x-axis, I've plotted the annual savings in fuel bills. A positive number means that a household saves money, and a negative number means that a household loses money. On the x-axis, you have the benefits from reduced air pollution. So this includes both criteria and greenhouse gas pollution. And if you're above the 135-degree line in this case, society as a whole has a net benefit by switching to heat pumps. So you add the private and the societal benefits, and they're positive above the 135-degree line. Interestingly, there are a number of places where heat pumps would actually save people money, but produce an adverse environmental outcome, basically by increasing criteria pollutant emissions. There are no situations where the public benefit exceeds the private benefit. There are no points between the 45 and 135-degree lines. And so this shows that there are no places in the US where there's a case for a public benefit for heat pumps. So that is the story today. How would things change if the grid got substantially cleaner? One scenario that envisages such an outcome is EPRI's transformation scenario. Under this scenario, electricity generation would decarbonize fully by 2050. This requires that the CO2 intensity falls by 9% per year each year from 2015 to 2050. And we assume that the fuel switch that is needed to achieve this causes the intensity of other pollutants to fall at the same rate also. After 2020, the transportation or the transformation scenario assumes that there is a $50 per ton CO2 tax applied economy-wide, and this rises each year in real terms at 7%. So effectively, you're talking about a $400 per ton tax by 2050 across the economy. What you see here is the lifetime benefit from the change in criteria pollutant emissions from switching to heat pumps, and the lifetime benefits from reduced CO2 emissions. So on the y-axis, you have criteria pollutants, and on the x-axis, you have CO2 emissions. There is a slider here, which will move in a second, which shows you the year of installation of the heat pump. And what the numbers right now show you is that if you switch from natural gas to a heat pump for a typical single family home in the upper Midwest, say, which is the MRO region, that switch would increase total environmental damages over the lifetime of that heat pump, even if you assume that the grid got steadily cleaner. Now let's look at how that situation would change with the year of installation. So watch the slider move. And what you see is that you get to about the late 2020s, 2030s before even the lifetime benefit of switching to a heat pump exceeds the environmental damage it does across the United States. This is somewhat sensitive to how you assume the heat pump is used. There are different ways of running the heat pump, which might produce a slightly different outcome. But the message is that in a number of places, even if you dramatically cleaned up the grid, there would not be a benefit, environmental benefit to switching to heat pumps today. Imposing such a tax would make electrification attractive, but it would increase fuel bills sharply, particularly in the upper Midwest. Given that the poor spend a larger proportion of their income on energy, this clearly has implications for equity. Also, it has implications for the political feasibility of a carbon tax that achieves this kind of electrification. So the upshot of this analysis is that the easy part of decarbonization, which is simply electrifying residential and commercial heating, depends on successfully achieving one of the hard parts, which is potentially decarbonizing load following electricity. On paper, a robust carbon tax would shift the incentives enough that people would electrify. However, it would be injurious to equity. It would produce disparate effects across the country, which suggests that people might actually resist this kind of a simple, robust carbon tax. With that, I'd like to thank all the organizations that have supported this research and would like to take questions.
Thank you so much. That was really, really great, Parth. Let me start. We have a bunch of questions coming in. Please submit your questions into the Q&A box below. Just as we're starting, one of my questions was, in your heat pump work, did you also consider the cooling of the heat pumps, the cooling
No,
functions?
no,
And
so
how would that have changed your results? Because I know a lot of them are used for both heating as well as cooling.
right. So that is potentially a double-edged sword. So on the one hand, heat pumps, because they're one, if you install them today, you would just install a new heat pump. And if you had an old air conditioner, the heat pump might be more efficient than that. So in this analysis, I've assumed that in terms of cooling, a heat pump is as efficient as whatever air conditioner you have right now. So I assume there's no benefit. In practice, there might be a benefit because being a premium product, being relatively new, it might be more efficient. The flip side of that is that there might be places where you either don't have air conditioning or use air conditioning very sparsely. For example, you might have places where you just install a window unit for a couple of months of the year. I know friends in Pittsburgh who do that. If you had a heat pump, they effectively have central air, and there might be a rebound from that. So there's a technical effect, which I assume sort of comes out in the wash, but there's also a rebound effect, which I haven't modeled.
Great, thank you. One of the questions that first came in when they were registering, can you talk a little bit about the differences for policy, costs, and logistics that arrive in different geographic areas? For example, rural areas, for some of your, I think this is talking probably about your autonomous vehicle work.
So for autonomous vehicle work, I think there's a number of equity issues, for example, that could be addressed by autonomous vehicles. So, for example, access to public transit could be provided by autonomous vehicles. Anecdotally, I've heard of experiments where transit agencies effectively give people credit to use on Uber or Lyft, and that sort of arrangement would obviously become cheaper if you had autonomous vehicles. So that might be possible. Again, the flip side of that is, to what extent do they affect the finances of transit companies by cannibalizing demand in urban centers? So what is the balance between those two systemic effects?
I guess, what about for rural areas? I mean, up in Hanover, New Hampshire, where Dartmouth is, we don't have Uber, we don't have Lyft. There's very little charging infrastructure. How do you think about that infrastructure affecting the big parts of the country that don't have kind of the urban infrastructure to support necessarily the types of advancements you're talking about? There's a few buses running around. I will give a shout out to Advanced Transit.
Right. So there, I guess you would separate electrification and autonomy. It may be that electrification is harder to achieve for other reasons. For example, if you don't have charging infrastructure, but autonomy would produce a benefit in that autonomous vehicles could effectively fill a gap that would otherwise be filled by transit, for example. So that might be a net benefit, and that might be a case where you might want to, at least initially, introduce automation without electrification. There's also a resilience question there. If you move a substantial part of your transport to electricity, and you have things like outages and so on, then are you stuck in a situation where an electricity outage actually affects people's mobility, for example?
No, that's a really good point. There was a question, as there always is when the topic is EVs, and I think you can nip this one in the bud, of just about the scale of battery production and cost of batteries.
This does not touch upon that. There's a plethora of academic work that studies that, and there's a bunch of non-academic work that speculates on that. So that
where is your opinion as to where this is today? As somebody who thinks a lot about these technologies emerging and where the state of the art is.
I don't know because I haven't done the work. So I can report on studies that I've read. And there's one school of thought. There's work that actually came out of Carnegie Mellon, which suggested that enough of the cost of lithium-ion batteries came from things that weren't subject to economies of scale. So things like materials and so on, that increased output would actually not dramatically reduce costs. But on the other hand, there are those in industry who actually do think that costs will come down to below $100 a watt hour. So I haven't done the work, so I don't know, but there are different opinions on this. It is also the case that some performance is being squeezed out by better battery management, by more efficient drivetrains. So there is all of that also.
With the other, one of the questions here about the heat pump work was, have you compared the customer economics, the upfront cost or net present value of heat pump and gas heating? That seems to be a barrier for switching from gas to heat pump.
Yeah, so I deliberately didn't show that. Part of the reason is there isn't one cost associated with switching to heat pumps. It matters whether you're doing a retrofit. It matters whether you're doing a new install. And broadly, the answer is that if it's a new install and you're installing a heat pump for both air conditioning and heating, then it is cost effective to actually have a heat pump instead of a furnace. But if you're doing a retrofit and there's an existing air conditioner, then it is not. The other point that is worth making here is that some of this modeling or the modeling that I presented assumes a hybrid heat pump gas solution. So you do have situations, particularly in the Midwest, where the demand for 10, 15, 20% of the hours every year exceeds the heat pump's capacity, and the heat pump would basically become a resistive heater. So I assume that when you get to a point where you've hit capacity, you back that up by natural gas. And so then if you had to have a hybrid solution, then the economics from the point of view of an individual don't work out very well at all. That said, in places like California, in places like the Pacific Northwest, the economics work quite well because it doesn't get cold enough for you to need that kind of hybrid solution. You're effectively never using natural gas. And there, along with the capital cost of the heat pump things, the economics from a private householder actually work out okay.
It's interesting to think about. Yeah, do you have anything to add on that, or?
Yeah, one more point. So I think the most, assuming no carbon tax in today's world, the most that you can get in terms of reduced energy bills from heat pumps is about $4,000 or $5,000, and the median amount is about $1,500. So that median amount is not enough to pay for the installation of a heat pump if you weren't also getting air conditioning, whereas $5,000 is.
Yeah, that makes sense. I mean, I know that up in northern New England where we are, there is no natural gas network. And so people are usually using electric gas heating or oil tanks. And so the heat pump plays a different role there. And you mentioned some of that research. Could you speak a little bit more to that?
Yeah, so I'll mention two things. One, to speak directly to your point, I'm working on a study with Lucy Chu, who's at the University of Maryland, who has Zelo's database of every home in the U.S. And Lucy has mapped where the heat pumps are and they correspond to exactly what you're saying. They are where you would expect the gas network doesn't reach, and people have sort of figured out that it's cheaper to have heat pumps. Yeah, so I think that's exactly right. That and the other thing that I want to mention, which is also future work, is that within cities, in this study, I've modeled a typical single-family home, but of course, there's a distribution of households, and we are in the process of writing up a study where we actually look at the distribution. In terms of studies that have looked at other fuels, Seth Blumzak has a study which looks at a ground source heat pump at his house in central PA. There are a couple of other studies which look at which treat the CO2 emissions from your current heating source parametrically, and treat the CO2 emissions from the heat pump parametrically, and you can then work out what belongs where and where, where in that curve you would be if you were using natural gas, for example.
That's really interesting. One of the questions here was about the distribution grid and how much electrification of EVs and heat pumps can a typical US distribution grid handle?
So for EVs, I don't know the answer. For heat pumps, again, let me see if I have the chart. If I don't, I will just speak to the numbers. Yeah, I think there it is. Yeah, so if you have the type of hybrid solution that I described, where you use natural gas and a heat pump, in a number of places in the US, you would sharply increase hourly peak demand. Because this is largely driven by the weather, this would be coincident demand. So I don't know how much slack there is in the distribution network to accommodate this increase, but it would be challenging if everyone switched to heat pumps. And this again is something that we're working on right now, and we're trying to put numbers on what the effective cost would be. If you switched to a fully heat pump solution where you had no natural gas backup, then you have a dramatic increase in peak. So you go from 3, 4, 5 kilowatts to 10, 15, 20 kilowatts. And of course, that has consequences for the distribution network. What's worth noting is that in a lot of these places, you go from a traditionally summer peaking system to a winter peaking system, and maybe the electricity system has a bit more slack in the winter than it does in the summer. So it's complicated, but you undoubtedly have a big hit on peak demand.
And Parth, what might be kind of fun to model in the future, I'm just thinking about when I lived in Minnesota, we had a heat pump, but it was also part of Xcel Electricity's demand management program. And yes. So thinking about how that technology can integrate with utility demand management programs may give you some really interesting angles for both the peaking issue, but also the grid flexibility questions that you might need for other resources.
So that's exactly what we're doing now. This work is supported by Sloan, and this was the first year of work. The second year of work is the answer to that question. What if we added thermal storage? What if we use the inertia of the building to shift load, which is basically allowing the house to get warmer when electricity is either scarce or dirty or expensive? And
so we can plan on having you back next year then to tell those results. That's really interesting. And I'm happy to send you some more resources on that, because I think it's a really cool question. I have one more question, and then I want to give you a few minutes to wrap up and then just close. One of the major concerns with using driving cycles is that oftentimes the results are not completely representative. There's been a big push to include real driving emissions with portable measurement systems within the regularity framework for fuel economy emission testing. Are there no real-world tests by OEMs, independent testing labs, that confirm the stimulating conclusions of the paper for real driving conditions? That was Prabhat Hedge who's asking this question.
Yeah, so I mean the issue identified is correct. The driving cycles are not representative of real driving. So we've dealt with that in two ways. So one, the physics-based model has been calibrated so that it gives us the numbers that the EPA has for driving range. You could argue, and I think argue correctly, that those numbers are not representative of real conditions. What we are trying to do, though, is trying to look at the difference between autonomous and electric and just plain electric vehicles. So we're hoping that the difference is not as badly affected by the fact that these things are not representative. So the absolute numbers may not be right, but the relative numbers should be in approximately the right ballpark, because there are errors on both sides which hopefully cancel out.
That's really helpful. I wanted to give you just a second to wrap up. There's one more question, but I'm going to let you take that one offline. Where are you going from here? Tell us about some of your big research ideas. Then I need 2 minutes at the end to kind of just wrap us up. So 1 minute to just tell us what your future plans are.
So some of the things that you mentioned, trying to look at if you autonomously try to control people's demand of electricity for the benefit of the grid or for some social objective, what are the benefits and costs and trade-offs involved in doing that? Are there considerations of equity? Are there considerations of privacy? So for example, if I give you a lower electricity rate, but have the right to really control your thermostat and turn down your heat in the dead of the winter, you're more likely to accept that trade-off if you were already spending a large part of your income on electricity or on heating. So what are the equity implications of some of the ways in which you can manage the demand that emerges from this? How does autonomy interact with public transit? And also, I saw that there was a question about trucking, which I'd love to talk about offline, but trucking is a big part of what we're doing next.
Yeah, that's good. There was a question on trucking, so we'll send you the rest of those questions. And Stephanie, could you show the slide? Thank you so much, Parth, for today. It was just great having you here and really interesting to think about some of the challenges with the electrify everything kind of mantra that is so often shouted forward. So I had asked Stephanie to prepare a slide of future events. On Thursday, July 14th, the Dartmouth Energy Collaborative will be having a talk with Jeff Daigle from PNNL, Abby Hopper from the Solar Industry Association, Tom Kernan, head of AWEA, Dan Riker, and Sue Tierney on energy stimulus, investing in electric power. So this is a really good conversation among some senior thought leaders across solar, wind, cybersecurity, policy, and economics. So we're looking forward to that conversation on the 14th. Our next new energy conversation will be with Rebecca Sia's, co-hosted in particular by the Andlinger Center at Princeton, and that will be hosted, I think, by Lynn Liu. And then there's another collaborative energy series where Catlin Bunker from the Rocky Mountain Institute will be talking about clean energy transitions. And so there's the idea of partnering with Caribbean islands to develop inclusive approaches to going forward. So we wanted to thank everyone for being part of this conversation. We look forward to having you come to the next new energy events. You're welcome to all events, of course. And if you have any other ideas or suggestions for speakers, please send them to me. We're happy to kind of keep the list going. We have kind of this term filled up, but we will hope to be doing this in the future as we go forward and hear the really exciting research from our young energy professionals coming out. So thanks, everybody. Have a good rest of your week and happy 4th of July.